Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra chapter Eigenvalues and Eigenvectors. Lecture number 8, in which I will prove more theorems on characteristic roots of special type of matrices. Now we prove a theorem. Theorem is the characteristic roots of a Skew-Hermitian matrix are either pure imaginary or zero. Now we prove this. Let A is a Skew-Hermitian matrix. Therefore, a to the power theta equal to minus a. This is number 1. Now, IA whole to the power theta equal to, this means I conjugate and a theta. This is equal to I conjugate is minus I and a to the power theta equal to minus a equal to IA. Therefore, IA to the power theta equal to IA implies that IA is Hermitian. We know that characteristic roots of Hermitian matrix are all real number. Let lambda be a characteristic root of the Skew-Hermitian matrix A, and let X be the corresponding characteristic vector, then AX equal to lambda x implies that I multiply AX equal to I multiply lambda x implies that IA x equal to I lambda x implies that I lambda will be a characteristic root of IA. Let this is number 2, this is number 3, and this is number 4, implies that I lambda is a characteristic root of Hermitian matrix IA using theory. In theory, we have seen that IA is Hermitian. If A is skew-Hermitian, implies that I lambda is a real number, because the characteristic roots of Hermitian matrix are all real numbers. This is real, implies that lambda is 0 or purely imaginary. If lambda equal to 0, implies that I lambda equal to I multiply 0 equal to 0, a real number. If lambda equal to IA, A belongs to real number, implies that I lambda equal to I into I multiply A, lambda equal to IA, and this will be equal to minus A real number. Implies that if a lambda IA, this is pure imaginary, is purely imaginary, then I lambda is real. Let this is number 5 and this is number 6. Therefore, from 5 and 6, we get that lambda equal to 0 or a purely imaginary number, implies that the characteristic root of Skew-Hermitian matrix are either 0 or purely imaginary number. Proved. Now we prove the next theorem. Next theorem is the characteristic roots of real skew-symmetric matrix are either pure imaginary or 0. Now we prove this. Let A is a real skew-symmetric matrix. Therefore, each element of A is a real number and transpose of A equal to minus A. This is number 1. Since each element of A is real, implies that conjugate of A equal to A, This is number 2. Now a to the power theta equal to conjugate of A transpose, and this conjugate of A is A transpose, and A is skew-symmetric, so A transpose equal to minus A. This is number 3. Therefore, from 3 we get that A is a Skew-Hermitian matrix. Since we know that characteristic roots of a Skew-Hermitian matrix are 0 or pure imaginary. Therefore, the characteristic root of A are 0 or pure imaginary. A is real skew-symmetric matrix, implies that the characteristic roots of a real skew-symmetric matrix are pure imaginary or 0. Proved. Now we prove the next theorem. Next theorem is the characteristic roots of a unitary matrix are unit modulus. Now we prove this. Let A is a unitary matrix. Therefore, A to the power theta multiply A equal to unit matrix. This is number 1. Let lambda is a characteristic root of A and x be the corresponding characteristic vector. Therefore, Ax equal to lambda x implies that Ax to the power theta equal to lambda x to the power theta implies that this means x to the power theta a to the power theta equal to this is lambda conjugate x to the power theta. Let this is number 2, this is number 3, multiplying 3 and 2 we get 3 is x to the power theta, a to the power theta left side, and left side of this is ax, left side is lambda bar conjugate, x to the power theta, here lambda x, implies that x to the power theta, a to the power theta, a x equal to lambda bar conjugate of lambda, lambda, then x to the power theta x implies that x to the power theta, a to the power theta multiply a is unit matrix, x, this is lambda bar multiply lambda is modulus of lambda square, x to the power theta x, in left side this is a to the power theta multiply a equal to unit matrix using 1. Implies that this is x to the power theta multiply unit matrix, this is x to the power theta multiply x equal to modulus of lambda square, x to the power theta multiply x, implies that x to the power theta multiply x, here modulus of lambda square minus 1 equal to 0. If we take this quantity right side, this is number 4. Since x to the power theta multiply x is not equal to 0 matrix, therefore from 4 we get modulus of lambda square minus 1 equal to 0 real number, implies that modulus of lambda square equal to 1, implies that modulus of lambda equal to 1. Therefore, this lambda is characteristic root of unitary matrix. Therefore, characteristic root of a unitary matrix are unit modulus. Proved. Now we prove the next theorem. Next theorem is the characteristic root of an orthogonal matrix are of unit modulus. Now we prove this. Let A is an orthogonal matrix, implies that A transpose multiply A equal to unit matrix. This is number 1. Since each element of A is real, implies that A bar conjugate equal to A. This is number 2. Therefore, A to the power theta equal to conjugate of A whole transpose, and this equal to A bar equal to A, transpose. This is number 3. Therefore, a to the power theta multiply a equal to a to the power theta is transpose of a multiply a equal to unit matrix I. Here using theory and 1. Here a to the power theta equal to transpose of a using theory, and multiply of these two is unit matrix I using 1, implies that A is a unitary matrix. In unitary matrix, a to the power theta multiply a is unit matrix. We know that characteristic roots of a unitary matrix are of unit modulus. Therefore, characteristic roots of A is unitary matrix here, are of unit modulus. But actually A is orthogonal matrix. Since A is originally orthogonal matrix, therefore the characteristic roots of an orthogonal matrix are of unit modulus. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button, and if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.